Yes, thank you very much for inviting me, and thank you very much, Professor, for the very good souvenir. I think the funny thing is that much more happened in our head during my thesis presentation than on the board itself. so, so this is fantastic because most of the ideas we had in the recent years were based on the philosophy that I learned with you in Udine, in Italy. That is the philosophy of seeing the forest first and the big picture first before the tree. And I think that for young people listening today, don't get too busy with every tree if you don't know what the forest looks like, because that's the first place to watch. Okay. So thank you very much. So I'm going to summarize today the status of knowledge, and I'm going to present you some pretty recent stuff. I have no conflict of interest with the gpexe company, so I don't earn money if you buy some GPS units. That's very important. But it allows me to say when things seem accurate and correct, and it allows me to say when things aren't. And so far, I'm very, very happy and positive with the gpexe data and things. So thank you also for the possibility to present. So for those who missed the first episode, because what happened previously was that we presented the method, we presented the concept, and so today I will present the applications. But I'm going to provide a quick summary of the method itself. I think most of you are aware about what we call the classic linear sprint force velocity profile. So this is pretty well known now. It's something that was existing for years, but it's something that we have developed with my colleague Pierre Samosino using some speed or position measurements. And you can assess the velocity force profile. You can use it in rehab, monitoring, training. There's been, I think, something like almost 15 years of research around that, and also in injury prevention. And if you want to know more, you can go to my website where you can see some blog posts and some discussions around that. But the very important thing is that picture here on the top. The thing is that if you want to record that profile and use it, and many people use it actually, there's one limitation. You need to run a test, because you need players to go from 0 to top speed linearly, and it takes a warm-up. It takes 30 to 40 meters for some, and it's a stress. And I have extensive experience in testing athletes. I think over the hundreds of athletes I tested myself, or my students or my colleagues, nobody ever injured during testing, but still, it's a stress. So the idea was, we had two solutions. We could tell the coaches, that's the way it is, and you should do a test, or we could try to find something to go around that testing thing. So that's something we've discussed, and this is the type of meeting in the COVID era times. So some people on their terrace, some others in their office, and we've discussed that with the team here. And so Professor Christian, Pierre, Jan, and collaborators Alessandro and Barnabo. And it was accepted in the Journal of Biomechanics last week, and it's going to be published as this paper, Individual Insitu Profile. So I'm going to present that. If you want to download an accepted version of the paper, you can go to my ResearchGate. It's online now. So the overall idea came from the discussion with Professor Di Prompero about measuring the energy cost of sprinting, because this is still something we cannot do directly, because energy is multiple pathways, as you know, in sprinting. And one day, Professor said, don't worry, you just have to measure all the oxygen. If you measure all the oxygen represented by a single sprint, then you have an idea about the cost of the sprint. But of course, all the oxygen is difficult to measure. So here it's exactly the same idea. The approach is measure all the data of a session, a game, a week, 2 weeks of training, and then you plot the speed versus acceleration data. So this is only 1/2 of the cloud, because the negative accelerations are not displayed. And what we observed is that, so this was done over 2 weeks. So this is 2 weeks of data. That's something like 1 million points in a pro player. And what we observed is that for each speed, this is connected to what Professor just presented. For each possible speed, from 3, which is slow jogging, to the top speed, there is a maximum acceleration capability that the player was able to produce. And this is decreasing linearly with speed. So it means, and everybody knows that, when you run fast, you don't have a big acceleration kick. But when you run slow, you can do more. And at the end of the day, when you plot the speed versus maximal acceleration in your cloud of data, you have something that's linear. You can optimize that with removing outliers, of course, but eventually you find this regression line. And if you extrapolate the line, you have the theoretical maximum acceleration, A0, and the theoretical maximum speed, S0. All right? So this is the profile of the player. And again, to get that profile, I didn't ask anything special to the player except playing. So it means it's a total passive data collection. So if you want to know more, you can go online and watch again these presentations. So just for you to see how it's done, because most of the questions I had so far, sorry, I'm gonna, okay. So here, this is the web app of the gpexe system. So once you have uploaded your session, you can open the web app. It will show you the session. So classical metrics, distance, time, power, speed, events, whatever. This is the speed trace of a 45-minute training session. And if you go to the details, you can run. So you select the dates you want to build your acceleration speed profile on. So I select only one day because I did only a 45-minute all-out football session. Then you select the player, and then you export the acceleration speed profile. So this is how it's done. It's a few clicks for the coach. And as you can see here, the web app is going to generate the acceleration speed cloud of data that will end up being my acceleration speed profile on that day during that session. So here you see only the final points, but here is the cloud of points. Okay, so a few points were removed as outliers, but only just maybe 2 to 10. And if you don't have the gpexe system, we have generated a website that is now open, and that will allow you to upload your time, speed, acceleration data as a CSV file. So you can export your data from your system, import it into our open website, et voila. This is your acceleration speed profile coming from your CSV file. So I want to thank Yann Lemat, who is a young PhD at my lab, who designed this website, because if any of you is able to use it, if you don't have the gpexe system, that's thanks to Yann. All right? So this is basically how it's done. Now let's talk about the comparison between the classical FV profile and the Insitu profile. So in that session, I zoomed on a single linear sprint that I did at some point in the session. So as you can see here in the raw speed data, 0 to maximum speed. So sorry for the 7.5 maximum speed, I'm getting old. And then I export the data to a very simple spreadsheet as the raw data, and then it's fitted with an exponential function and computed following the method validated by Pierre Samosino. So the idea is that on that day, on that sprint, my acceleration speed profile was very, very, very close to the football one. So you need to understand here the connection, because conceptually, it's exactly the same. What my body was able to produce in terms of acceleration on that day was either collected through my many, many football movements or through a single linear test. And the data ended up being very close. So we need to test if it's the same on every player, but for now, the concept is exactly the same. What acceleration or force can you produce at any given speed of the spectrum? So at the end of the day, the idea is very simple. You have two modalities to test about the same thing. One is the classical test, and the other one is from football or rugby or ice hockey or whatever data, provided you have accurate speed time data. Conceptually, F0, that is well known, and A0 are the same. it's your ability to accelerate in the horizontal direction. It is just two different units of the same quantity. And V0 and S0 are the same, except that one is taking air friction into account more than the other. So, like Einstein said, you can count some things that count. And so the idea is that if you want a specific test, do a specific test. If you want football-specific data, run the football-specific analysis. So now I'm going to show you 3 examples of applications. One is going to be monitoring, the other one assessing the effects of training, and the other one is using the acceleration speed profile in injury context. So at every step, I will explain briefly what we did so far with the classical linear test and the analogy that you can do with the acceleration speed profile. So in terms of monitoring, that's pretty easy. If you test throughout the season the players, and this is something we do in many clubs we collaborate with, you can exactly know how does the profile of the player change every typically 2 months. And you can do training content management by giving every player what they need in terms of weaknesses and strengths you want to develop. Of course, always in the context of their playing position and game demands. But you can also do what was mentioned here in this beautiful paper by Caroline Finch and colleagues. You can adjust the training loads to each player depending on their objectives, their status, and their training physical capabilities. So it's a good tool, in my opinion, to go more individual in how you manage the training content. So typically here, this is something that we did with Pedro Jimenez Reyes. This is the season measurements of a professional team in La Liga, so the first league in Spain. And we could measure the sprint profile of the players pre-season individually, not only for the group, but also individually. And we could see how these changed, the maximum force, the maximum velocity, and all the mechanical variables over the season. So this is important because in terms of training, you see that not everything remains constant throughout the season, and things change differently for different players. So the idea here, in my opinion, this is the next revolution of team sports, is to consider not only the group average. The group is nobody on a team. The group doesn't exist. Sometimes the group value is the value of no player. The individual is more important. So we have a tool to individualize things. Now let's see what we can do with the acceleration speed profile. So this is something I generated from a Serie A team. So the coaches and Christian shared with me 5 months of data for 15 players. And you can see here you have 1 point. This is the average of the team. So I just said we should not focus on the average, and I'm presenting you the average. But believe me, if you want every single player's graph, that's going to be a spaghetti plate. Well, you can enjoy spaghettis, but sometimes it's clearer to have the mean data. So baseline is the beginning of the season, and then you see the percent change in V0 in blue, so the maximum velocity of the average of the team, the maximum acceleration of force of the average of the team, and the slope of the profile. So it means the slope of the profile tells you if they are more force or velocity oriented. And what you see first is that there are huge changes week by week. So it means things change a lot. Every data is an average data for 1 week of football training, okay? And you can see that, I don't know if it's by random or if it's a tendency, but we need to do studies on that. But in that period where we have 2 big peaks of very fast V0 and at the same time very low F0 or A0, we have 3 hamstring injuries occurring. So of course, there's absolutely no causality shown here. But what I want to say is that you can perfectly fit the data with the injury history of the team. And this is, I think, something that will generate some thinking, okay? Because you know more what happens. And very importantly, over these 5 months of data, nobody ever did a sprint test. This is entirely football data. So the second thing I'm going to present is how to check and assess the training effects whatever type of training or detraining you want to set with the acceleration speed profile. So of course, I won't go into details, that would take hours and hours, but in the last 5 years, we've generated a lot of studies on training. I say we because that's mainly my group, but there's also some studies by Michiel Cahill, for example, showing what type of training input could influence, change what part of the profile. So this is the entire philosophy is, if I want to improve that part of my profile, what can I do? So this has been done with force velocity tests, classical tests. Now the question is, can we do that with the acceleration speed profile? So now I want to thank Alberto Botter. I saw Alberto listening. Ciao, Alberto. Because he shared with us some data from his elite rugby team, the Benetton Rugby in Treviso, Italy. And he did a study on the effects of training that I will show you here. Just a very nostalgic note, but there you are, Alberto. This is a picture of Alberto doing some jumps in Udine 10 years ago. This was the study where we proved and we validated the optimal force velocity profile in ballistic movements like jumping with Pierre Samosino. So I'm very happy to see that Alberto is continuously contributing to research in sports science himself or as a coach. So thank you again. Okay, so the players, 12 players completed the study. It means that more players started, but as you know, in elite sports, sometimes you lose players along the way. So 6 of them completed a control period. So that was a few weeks of training like usual, so strength training mainly. And 6 of them completed a high resisted sprint training protocol. So it means they pulled very heavy in sprinting, that was in season. So the control group versus the heavy sled. And the duration of the program was 7 weeks. And the load chosen was the middle of the spectrum. So a load that corresponded to about 50% of maximum velocity decrease. So typically, I won't go into detail, but it's a load that's heavy enough to stimulate power output. So the pre-measurement were a single sprint test that Alberto could run. But for many reasons, as you can imagine in elite professional players, the post-measurement were not a test. The post-measurement were 1 week of in situ profile. So this is very interesting to me because it shows you that if you cannot run a test for many reasons, you can see the change in the profile of the players in a more specific way. So the data I'm going to present will show you how the profile changed as a specific rugby player. So we don't talk about linear sprint anymore. We talk about the field, what happens on the field. So V0, basically V0, nothing changed. The average of the group and the individuals didn't show a clear improvement or decrease in their top speed. So it's in kilometers per hour, but basically you see that nothing changes. So that's very important. It means usual SNC work did not improve top speed, but this is something we already know, heavy sleds in elite rugby players did not improve top speed. But it was not the objective. The objective of heavy sled was to improve acceleration and power, not top speed directly. So the A0 data showed that in the control group, there was a mixed effect. Some players decreased very much. Some others increased a little bit, but on average, there was no clear difference. Alberto did not run some specific statistics, and I did not want to run some specific statistics because I like when we talk about raw data. And when raw data speak for themselves, you basically don't need statistics. And here, the effect is pretty clear. In the heavy sled group, there was an improvement of maximum acceleration for all the subjects except this one, all right? But the average was pretty clear. And it was -4% on the control group versus +7% in the heavy sled group. So 2 things to remember here. Heavy sled improve acceleration, which doesn't do SNC, classical SNC training. This is no big surprise. But the very important, and I think promising thing, is that this is not a sprint acceleration. this is the maximum acceleration capacity of the players on the pitch. So it means very likely, as professor presented, for short distances, they were getting the ball first, they were tackling the opponent first, etc., etc. This has major specific consequences. If I'm a rugby player and you offer me a 7.4 instead of a 6.9 A0, I'm going to pay for that. All right. So that was an example of the use of this in training. But you can use it in detraining. For example, the players leave on an international break, the players leave on holidays, whatever, off season. You just need them to play again 1 week or a few very good intense sessions, and you know where they are. So this is very, very interesting, in my opinion. Now let's talk about injuries. So the prepare-repair cycle, so prevention and rehabilitation. The use of the sprint profile in injury prevention and rehab was mainly started by Jordan Mendiguccia. I saw his name. Ciao, Jordan. I hope you're okay. And in 2014, we did a study with Jordan based on the profile at return to sport. So it means when the players were okay by the staff, we measured their sprint acceleration profile, and we observed that they had a lower Pmax, they had a lower force capability than the other players, clearly, but they were able to sprint as fast as before. So this was a bit questioning, because it means that obviously the rehabilitation was not over, because, okay, their muscle was back and their feeling was back, but definitely their sprint capability was still off. And 2 months later, we tested them again, and the values were back to normal. So it means here we have something that was not ready a lot to back to normal. The second thing that we did is that we started collecting data, monitoring players, because if one day a player gets injured, then yes, you have the pre-injury data. So you have something to guide rehabilitation. So in this first case study, we observed exactly the same thing. The pre-injury profile of the player was something like 8.5 newtons kilo to 8.7 meters second. And post-injury, so of course, this is not the day after injury, this is post-return to sport, you see that the Vmax, sorry, the V0 was back to normal. It was running as fast as before in the end of the acceleration, but at the beginning, F0 was still 20% lower. So here, typically, the rehabilitation should focus on getting that back to normal. If you think that the pre-injury data is something that was normal, of course, but this is another question. So this is a clear use in rugby that I've presented a couple of times, but this was done in the rugby club of Grenoble by Patrick Chassin, who is a PhD student that we supervise with Pierre Samozino. And the staff agreed to rehab the player and to do a test at the end of the rehab. Because if someone says, the rehab is over, but please don't sprint, there is something wrong in the picture, okay? The rehab is not over if you're not able to sprint all out. So here, in agreement with the staff, we did a test, and we did not allow the player to go back to play until the test profile was back to normal. And as you can see here, on February 9th, he was doing this 8488, which was within the range or better than his pre-injury data. And then we said, okay, in that player, in that season, there was no re-injury at the hamstring. So I don't know if it's because of that. All I know is that it's a pretty simple, direct tool to add to the rehabilitation puzzle. Is your muscle okay? Is your muscle strength okay? That's not enough. Are you sprinting okay? Yes, now you can go. So this is an example now with the ASP profile. So this is something that was shared by Christian again. So this is a player, and in red you have his acceleration speed. So we are talking now about the Insitu profile, okay? There is no test. So this is how he plays in the weeks before getting a hamstring injury. And this is in blue, how he plays during the week of the return to play. So it's very simple. He has the green light on Monday. We use the GPS data from Monday to Friday, and we have this profile. As you can see, in week 2, in week 4, in week 6, the maximum speed is almost back to normal, but there is a clear gap in the maximum force output or the maximum acceleration. So I don't know exactly what was done in rehab here, but I would advise more work on the maximum force output if I want the profile to be back to normal. Obviously, that player on the pitch for short sprints, defensive actions, offensive actions, he was not able to be good in short, intense actions. So now I'm going to show you two players on the team I presented you before. This is some work we did very recently, but obviously that would require much more research, as you can imagine. But this is very interesting. Here you have two players who got a hamstring injury, and the blue line is their profile for the 2 weeks before. So because we know when they got injured, it's very easy to average the profile for the 2 weeks before. This is the blue line. Let's say that it's their normal or reference profile. And the yellow line is their profile at return to play. So it means they go to the rehab, they are off something like 2 to 4 weeks. Once the rehab is over, they come back to training, we put the GPS on, and we measure what's happening in football. So this is, they don't even know we are testing something, okay? So there's no stress with the test. What you see is that for both players, the top speed is back to almost normal for him, -6%, and normal or more, but we are within the unclear zone here, but speed is almost back to normal, whereas maximum acceleration is 40% off for this one and 7% off for this one. So in these two cases, we have the same scenario. Maximum speed is okay, but maximum acceleration is not, which has major consequences in terms of football playing, because on the pitch, very often, maximum acceleration is more necessary than maximum speed. That's a fact in football. But this is done almost passively. So before we go to the discussion and questions, and obviously we have many questions ourselves on that, I want to have a very important methodological note here. Be careful. All models are wrong, but some are useful. And sometimes what is wrong is not the model. What is wrong is the input data. And very importantly, if you have inaccurate inputs, GPS data, speed time data, then no way you can get accurate output. So this is very important because the model is based on the linearity between acceleration and speed and the extrapolated A0 and S0. So I'm going to show you some things I have seen already on social media, some things that people shared with me. So of course, I'm not going to name anybody, but I want us to look at the data. First, if you have this type of cloud of data, here, there is something wrong. So it means it is not physiologically possible to run at 8 meters per second. Damn, I would love that. But you cannot run at 8 and accelerate around 2 to 3 meters per second square. It doesn't exist. This is a motor. It's a car. It's not a human. So if you have this cloud of data at the beginning, of course, the linearity will not be beautiful and the extrapolation will mean nothing. But it's not because of the model. It's because of the cloud of data that was not accurately measured. Second thing, if you see this type of behavior in the data, it almost makes no sense. How can you decelerate? So the speed here, this is a single movement recorded, all these points. How can your speed decrease with a positive acceleration? It doesn't exist. If the speed decreases, the acceleration is negative, not positive. So this is strange. It's a red flag. Again, if you see this kind of data, of course, you can also fit a regression line always between points. It will always happen, and it will always give you A0 and S0. The problem is not that. The problem is that if the data are that noisy, you cannot trust the outputs. So I want to very, very importantly emphasize that. First things first, question your input data before questioning anything else. And I observed in the last 6 months or years, even there's some publications we are going to argue on that, where people tend to blame the model or blame the theory instead of blaming their data. I always say to my students, if you have a sports watch that give you a VO2 max of 150 milliliters minute kilogram, are you going to blame the concept of VO2 max? No, you're going to blame the sports watch. So this is what you should do first and foremost. So I advise that you check and you show the entire data cloud, because that's the beginning of the model, of course. And I will finish with this. Everything here seems simple. It doesn't mean it's easy, and it doesn't mean you can do it with any type of input data. So this is very important, because it's the basis of the entire method and in the interpretation of data. So if you want to train people, rehab people based off the acceleration speed profile, you want to make sure you measured it correctly. And that's my talk for today. Thank you.